Let's take a quick look here. I want to show you guys something kind of cool. This is not. I'm not going to do a lot with this. I could go through this in a little more detail than I'm going to, and take you through the whole kind of derivation of this rule. But I don't think it's necessary because it's so similar to stuff you've already done. Kind of think about the stuff we've been talking about. We've been talking about integration, indefinite integration, which is anti-differentiation, right? And let's just get this real clear. These are different. They look very similar, but remember, if you do a problem like this, if you do a problem like, well, let's pick one that, get a little practice here while we're at it. What do we want to do? Okay, first of all, what kind of take all the phones and all that stuff away. Everybody have a look up here and let's get this figured out. What kind of an answer am I going to get for that? Am I going to get a number or am I going to get something different? Something different. Okay, good. How would you describe what I'm going to get for that? Okay, yeah, there aren't limits of integration, right? So we're just asking for the family of functions whose derivative is the square root of 3x plus 1, right? Okay, now this is stuff we talked about the day before yesterday. Do you remember? Now this is one we couldn't have done prior to this week. What do we do with this one? We got a great new trick.
Your du dx.
Okay, we got to make a u substitution. Good, this is good practice. So what's our u substitution going to be here?
3x plus 1.
Good, good. We want to, and this is, once again, it's kind of a ephemeral kind of a thing here. How do you say exactly what you pick for your u? You don't. You just have to use your judgment. Usually the best rule of thumb is it's going to be what's inside of a function, the argument of a function. And what you kind of want to train yourself to do a little bit is ask yourself now, what's the problem here? What's holding me up? Why can't I do this integral? Well, because of that square root, isn't it? There's a bunch of stuff inside. If it was just the square root of x, we'd be fine. But it's the square root of something more complicated than that. And so that's the part that we need to simplify, right? So that's a good choice for u. So if u equals 3x plus 1, what's du? 3 dx. Okay, good. And so if we try to complete our substitution here then, we get, what's this part going to look like? Square root of u. Okay, and I'm probably going to write that as u to the 1/2. And then what about the dx? What's that in terms of u stuff? Okay, good. So we'll pull the 1/3 out front and put our u there. And from there, it's no big deal, is it? Right? What's the antiderivative or indefinite integral of u to the 1/2? Okay, good. So we're going to get a u to the 3/2, and we got to put that plus c, and then we get a 2/3 tacked on out front times a 1/3 is. Right, we had that 1/3 times 2/3, 2/9. Okay, so there's our answer. Last step. Yeah, good. We got to reverse that substitution and get back to x's. Right? So our final answer would just look like 2/9 times the quantity 3x plus 1 to the 3/2 plus c. Good. Okay. Right. And that's half of what we've been doing here for a while. The other half was of the definite integral variety, right? Where we're going to get back, instead of a family of functions, we're just going to get back a number, an area under a curve. Then once again, that relies on the same technique, this indefinite integral, this antiderivative. But there are some problematic cases where things just don't work. You can't do this process. You can't find always an antiderivative for every function. Kind of a mouthful to say, but not every function is integrable, is the math word we'd say for that. For example, and this seems really weird to me that this one doesn't work, but if we try to take the definite integral of the cube root of x, actually that's not a good one. How about if we take, this one always blows my mind, you can't do this one. It just seems like you gotta be able to do that.
How do you know if you're not able to do it?
Well, yeah, good question. I mean, right now, I mean, it's because, how do you know it's just too hard? Some of them, I don't know. Good question.
There's no way to look at that.
I can't remember. No, there's definitely a way to do it. I just can't remember right off the top of my head how you could go about doing that. There's something better than just we tried but couldn't do it. There really is. There are some tests for integrability.
So will the math just go on and on forever?
Well, no, it's just that you can't find a trick. See, that's like, for example, if we tried to do this. If we tried to do that, now, this isn't one, we could try a U substitution, couldn't we? We could try, and this is probably a good exercise for us, just to look at one that doesn't work. If I tried to make what would my U substitution be? X squared. So du would be, 2x dx. And so if we tried to make this substitution, we're going to get a sine of u. But then here's where we have troubles. The this is one, isn't it? Yeah, it is. If I try to complete this substitution, I'm going to get du over 2x. And I got an x on the bottom, and that's kind of the problem here. I can solve for x in terms of u. That's fine to do, right? I mean, I could solve for x, and I'm going to get plus or minus square root of u, right? I have to treat both cases. But the problem is, I didn't really help myself. I didn't get something that I can take an integral of. And you don't have very many techniques to rely on right now. But even the ones under the most, even after next year, after you've learned a bunch of techniques of higher integration, you're still not going to have one that's going to allow you to do this one. You're never going to be able to find a way to anti-differentiate this function. It just doesn't work. You just kind of go in circles and you never get anywhere. And so, there are a handful of those functions that just defy analytical techniques for integration. And so what do? Obviously, I mean, we can graph this thing. And very clearly, there is such a function as sine x squared. It exists. We can graph it. And it is finite, and so it has to have an area under it, right? Let's take a quick look at this. If we graph this guy, we can even do this integral in our calculator from 0 to 3 pi. I need to show you, this would be another good opportunity for me to show you something on the calculator. Oops. Didn't I figure out a way to, yesterday, I can never remember how to do all this stuff. Didn't I find a way to make just the screen big? Oh no, maybe not. Oh, there it is, large screen right there. Okay. So what was my sine x squared? Okay, we can graph this. We can do this two ways on the calculator. We can graph it. And let's do that first, how about? So if we just go, oops. That doesn't say sine. Do that. Sine x squared. Okay. And let's go to window, and if we're going from 0 to 3 pi, how about if I make x go from negative 0.2 to, what's that going to be? 3 pi is going to be about 10-ish, a little less than 10. So if I go up to 10. Okay, and then we'll just go, how about zoom fit?
It's kind of a weird looking function.
Is it oscillating function?
It's actually not oscillating behavior, but why is it going so fast? How come it starts to oscillate so fast there?
Yes.
How come? Because the x squared. Yeah, exactly. Good. Because as the x's get bigger and bigger, the sign is, well, the function inside the sign, the x squared, is making the numbers get bigger even faster, right? As x goes, I didn't say that very coherently. Let me say that again. As x goes from 0 to 1, the x squared part isn't doing anything too dramatic to that. It's going from 0 to 1, right? 0 squared is 0, 1 squared is 1. But as x goes from 1 to 2, the x squared is spitting out numbers from 1 to 4, right? That makes sense? As x goes from, etc., 2 to 3, instead of just going linearly from 2 to 3, it's spitting out values from 4 to 9, etc., etc. And so you might say that, and this is kind of how I would describe it, it's accelerating the argument of the sine function. Because the argument is what we're feeding, the numbers that we're feeding sine, right? And it's accelerating those because it's increasing the rate at which the sine is being fed numbers. And so that's why it starts to oscillate more rapidly, right? It looks pretty complicated, but our calculator will do this. If I just ask it to add up an area, I can just go, I'll do it up here. I can just go second, calc. Which one do I want? You suppose? Yeah, integral, right? 7. Okay, 7. Lower limit, I can just type it in. I could, I could trace along that, but why? I can just type in a number. I'll put in 0, hit enter. I want to see upper limit, so I'll put in 3 times pi. And I can literally just type in 3 times pi. And it's going to think. It's going to make it think a little bit, because that's a lot of moving around. But it will add that up, and it will give me an answer. Yeah, isn't that cool? Right? So it'll do that. Okay. So obviously, there is an answer to this. There really is an answer. It's just that the math gods in there, they got a good sense of humor, I guess. They didn't see fit to allow us to analytically take that integral. There's another way to do this one too on your calculator. I want to show this to you. You can also, because this is kind of handy. Sometimes you don't want to have to go through the whole hassle of graphing something. Yes, sir. Good question. Hold that thought. In fact, that's the topic of today. What we're doing today, our solution is not too dissimilar from what the calculator does. How we can come up with an answer too without the calculator. So if we just hit the math button and we go to, well, I think we have to go down a little bit. We have to go down to, I think it's probably something like FNINT, if I recall. Yeah, there's right there. Function integral or finite integral, I don't know what that means, but some kind of integral. That's the one we want. And then look what it does. See, it just gives us, it didn't used to do this, this is really slick though, it just gives us this template that just matches what a definite integral looks like. So then obviously, that's pretty straightforward. We're just going 0 up to 3 pi, and then sine x squared dx. Right. And if I hit enter, it'll think about it for just a second, but it's a lot quicker doing it this way. Well, maybe it's not. I thought it would be. The D's already there. You just fill in the blank. Yeah. And it gives you the same answer. Okay, so how does it do that? It's relying on the same kind of technique that I'm going to show you guys. It's a numerical method. Now, this is a big deal. Not that this particular method is such a big deal, because honestly, most of the time, if you need to get an integral, you're just going to do what we just did. Calculators do this more accurately and easily than I'm going to show you, but it's important that you understand the concept of what a numerical process is. Analytical means exact, essentially. I mean, when we do stuff like this right here, that's analytical, right? Analytical means we used algebra and calculus to get the answer, right? The answer, and that's it. There's no dispute. I mean, that's the answer. if we did, like if we went back to one of the examples of definite integrals that we did over the last few weeks and we got an answer using integration, that's it. That's an exact answer. That's analytical. Numerical is not as satisfying. Numerical is something where we're going to have to use the power of lots and lots of numbers. In our case, we're essentially using the power of adding up lots of shapes under a curve to get a very good approximation of what the answer is. But it's not going to be exact. Now, we can control how exact we need it to be, and it takes a little more work to get a more accurate answer. But it's still never going to be exact. It's just always going to be an approximation. And that's what a numerical method is all about. Numerical methods are, that's in a way, like I said, they're not as satisfying because you don't get to say, that's it. That's it. It's just kind of, well, that's approximately it. But really, that's the way the world works. And like in physics, which is much more applied, almost everything is numerical. It's very rare that you're getting an exact answer. You're almost always trying to find some approximation that's good enough. And what's good enough sometimes is, you'd be surprised what's good enough. This sounds probably weird to you guys, but physicists a lot of times, if they're working on highly theoretical stuff, if you get within an order of magnitude, which means that your answer is less than 10 times, that the answer isn't more than 10 times different than what you got. It doesn't seem very good, does it? A lot of times that's fine. That's good enough. I mean, if we're trying to find, for example, the speed of a photon in the center of the sun, we have no idea initially, but if we can get that within a factor of 10, that's not too bad. That's not too bad. And then eventually we'll kind of, we'll narrow that down and get it closer and closer. But numerical approximations just all depends on what the context is. Sometimes they don't have to be as accurate as you think, but they're very prevalent. That's what we do a lot of times. So how do we do this? Well, how do you think you're going to do this numerically? If I wanted to, let me pick an example here. If I wanted to do something like, I don't want to do a trig one. How about if we just do, well, yeah, let's do a trig one. Why not? What if we wanted to, let's do one that we could normally do. What if we wanted to approximate sine x, the area under a sine curve, from 0 to pi, pretending that this didn't work analytically? How would you do it? What do you think? Because we've done this kind of stuff, haven't we? We really did, right? We did this kind of stuff already before I gave you the trick. You guys were adding up areas under curves. How'd you do that? How did you add up areas under curves before I gave you the adding up the circumscribed or inscribed areas using shapes, right? And the shapes we used were close enough. What were the shapes we used? Rectangles, yeah. Now rectangles were not bad, right? They were certainly better than some other choices we could have made. But we talked about some other ways that maybe rectangles in a pinch. Maybe rectangles aren't the very best because they're always flat on top. But the nice thing about them, say it again. Okay. No, the better choice might be, that's still really simple, might be a trapezoid, right? Because if we were looking at an area under a curve, something like that, and let's just, I'm not going to get into too much detail. You've seen me draw these pictures ad nauseum, so I won't make this too long and drawn out. But if these are the slices that we're making, right, through this function, if we make rectangles, they don't always fit so well, do they? Right? The advantage being, and you probably remember this discussion, the advantage being that the areas are so easy to calculate, right? Because it's just length times, or width times height, and that's it. So it's easy to add up, and that's the advantage. Disadvantage being they don't match the curve very well. Well, we'd rather, if possible, doing numerical methods, and this is how your calculator does it, by the way. Your calculator finds, like I think some of the newer ones, the TI-89 I know does this analytically, uses a computer algebra system, but the 84s don't. The 84s are numerical. Everything they do is numerically based. And so they're just using some kind of a numerical approximation method for finding all these answers that they give you so fast. And when they're thinking about it, they're just executing the routines that add up those areas. That's what they do. Can we pick one, maybe, that's still relatively simple, right? We don't want to pick something that's too hard. If I try to pick a shape that's got a curvy top on it, that's gonna be a harder formula to use, a much harder formula to use. So if I can pick one that's still an easy geometric formula, not something that I'm gonna have to go through and do a huge calculation for every time, that might be to our advantage. Well, why not just split the difference? Instead of just going straight across, why don't we just make trapezoids? Look how well those tend to match the curve. Pretty well, right? If I make those intervals pretty narrow, those trapezoids, even though it still is like a jagged sawtooth, they match the curve pretty well, right? And so that's what we do. And we develop something called the trapezoidal rule, for lack of a better term. Yeah. Now the trapezoidal rule, and I'm not going to go through, we've already done enough of this. I don't feel like we have to go through and derive what this rule is based on adding up areas. We've spent enough time on that. You get how that works. I'm just going to give it to you. The trapezoidal rule is just a formula that we can apply, just like we came up with a formula for rectangles, that tells us the approximate area under a curve for n trapezoids. Cut it into n trapezoids. And this is it. I'll get rid of this guy. Oh. Here's the trapezoidal rule. I remember that. Look in the book. Integral of f of x dx from a to b is. I'm going to write this two ways. Now, one way is just as a long sum of terms, and then we'll pare that down and write it using sigma notation, so we can write it more compactly, a little better way. But one way we do this is like this. So the width of each interval is going to be b minus a over 2n, I believe, times sum of terms. Now, the thing about the trapezoidal rule is when we're calculating the areas of trapezoids, remember what the area of a trapezoid is. It's height over 2, right? Remember this one? Height over 2 times the sum of the bases. One way of writing it, just the actually it's really the height times the average of the bases, b1 plus b2 over 2. But our trapezoids are turned kind of sideways, right? So that's really b1 and that's b2, and this is what we call the height in our traditional formula, right? And you don't need to be worried, you don't need to be writing this stuff down. But the point is, when we add all these things up, would you agree that the second trapezoid B1 is what B2 used to be, right? Does that make sense?
Yeah.
And then et cetera, et cetera. Now the only ones that aren't going to be double counted then, the only heights that aren't double counted are going to be the very first trapezoid, right? Because the left one only gets used once, and then the very final one, the right edge of the last trapezoid only gets used once. But every other side of a trapezoid gets used once as a right edge and once as a left edge, right? And just the only reason I tell you that is so this, as I give you this formula, it kind of makes sense. The first term is just going to be f of a, essentially, which we could call f of a or f of x sub 0. I'm going to call it f of a. Same thing as x sub 0 plus the next height that we have is going to be f of x sub 1, and that's going to have to show up twice because it's going to be used once for this trapezoid and once for this trapezoid. So all these other ones are going to get these coefficients of 2 on there. We get 2 times f of x sub 1 plus two times f of x sub 2 plus all the way out to this next to the last one, right? So I'm going to go clear out to 2 times f of x sub n minus 1. And then the very last one, I only single count. F of x sub n, which I could also call b if I want, right? Because this is really, remember, that's just my first x value, and that's my last one. That's the trapezoidal rule. It's not that complicated. That's it. Okay, the width of the intervals, b minus a over 2n times the sum of all those heights, and we have to double count all the interior ones. We'd say that the extreme ones, the first and the last, don't get double counted. But one way to describe this is as the interior sum. Okay? All the terms that aren't first or last get that coefficient of 2. Right? So we could make this a little bit simpler here. We could write this using sigma notation as b minus a over 2n times f of a plus f of b plus that interior sum, right? Wasn't that interior sum just 2 times f of I, right? F of x sub I, as I goes from 1 to n minus 1. We could pull the 2 out front of the sigma. Right, not to n minus 1. Does that make sense? Right? Because we're only attaching that 2 to all the terms except the first and the last. Right? Now, remind me, and this hasn't changed, what is x sub I? X sub I, that's the same as it always has been when we talked about rectangles. X sub I is that's just what's the x value at the end of the ith step. So what is x sub I? Where do I start?
B minus a.
Well, no, I start at a, right? Because a means that's the left edge of the interval, right? So if this is the x-axis, I'm going to start at, maybe the origin's back there, but I'm starting at a, and then I'm going to take I steps, or n total steps, right? Sorry, n total steps to get to the other side of the interval, and those are going to define the width of all those trapezoids.
Was it a plus n plus I?
Okay, so it's a plus I times the width of my steps, which we might call delta x, right? So it's a plus I delta x, right? And just think about those as my steps. There's my starting point, and these are just how far I've walked after I've taken I steps, right? And what's delta x always?
B minus a divided by n.
Yeah, it's just the width of the interval, right? Which is the total width divided by the number of steps. So all that stuff is still the same. You've already done all the hard stuff. This is way easier than what you did earlier. So really then we could just always write x sub I as a plus I times b minus a over n, right? Okay. And that's how we do it. That's our formula, right? Very, very similar to what we did before. Okay. Let's try an example. Okay, what if we wanted to, well, let's go back to our sine example. If we want to use the trapezoidal rule to approximate that, how about, and let's just use n equals 4. Actually, we don't, n equals 4 is boring. Let's do n equals 40. So what would we do? The area by the trapezoidal rule. Do you remember the formula?
H divided by 2 times Q.
Say it again.
H divided by 2.
Oh yeah, okay. Okay, but how about the trapezoidal rule formula?
Oh, that's wrong.
Yeah, it was. We had b minus a over 2n,
Yeah.
right? So that's going to give us pi minus 0 over 2 times 40, right? Times f is sine, right? So sine of 0 plus sine of pi, right? Plus 2 times the sum of sine of a plus I delta x, right? So let's maybe figure out what that is. So x sub I equals a plus I delta x. So for us, that's going to be 0 plus I over pi I over 4, right? Isn't delta x just pi minus 0 over 4, over 40, whoops. Not 4, 40, right? B minus A over N. So we're going to get 0 plus pi I over 40. So that's it right there, just pi I over 40. Okay, everybody with me? That make sense? So that's what we're going to be feeding into the sine function in our sigma. So we get sine of pi I over 40 as I goes from what to what? There's n trapezoids. So we go from our first trapezoid to 39. Good. Remember, it's n minus 1. We're only adding up n minus 1. So that's it. Okay, we're going to do this. Here's the good news. You get to use your calculator to do all these. Because this is a numerical method. This is not an analytical method. So you can use your calculator to do this. But on the test, the right answer is the wrong answer. On the trapezoidal rule, when I'm asking you to use the trapezoidal rule to make an approximation, it's not going to be the same answer that your calculator gives you for the area under the curve, because that's going to be more accurate. The trapezoidal rule for n equals 40 is not going to be perfect. It's going to be a little further off than what your calculator would tell you. Right. So you actually do have to use the trapezoidal rule to get that right, wrong answer. You know what I mean? So let's, yeah, exactly. So let's try this. So oops. There we go. Okay, so let's try this one then. So if we want to add this whole thing up, let's practice putting this whole thing in at once. Okay. So I'm gonna put all this stuff out front, right? So I've got the fraction pi divided by 80. Pi divided by 80. All right, everybody sees where I get that, right? Times, now what? What do I got? Tell me what keys I would push on the calculator to do this one. Okay, but before I do that, remember, this is the coefficient of all these terms, right? It's being multiplied by this huge quantity. So what do I got to be real careful about doing here? Parentheses. Got to open up a set of parentheses, don't I? Right. So I've got the quantity sine of 0, and I could just, we all know what that is, but I could also just plug these in, plus sine of pi. Once again, we know what that is, but plus, now what? Now I get down to this part. Yeah, good. 2 times. And now I can do this sigma notation, right? I can go, what is it, math? What was it, 0? Math 0? Okay. Math 0, yeah, that gives us,
You gotta scroll up.
there we go, okay. And we'll just call that x about. X equals, goes from 1 to 39, good. And what is the argument of our sigma? What are we adding up? Well, that, right? Sine of the quantity, and it's already given me the quantity there. Pi times I, or pi x, right? We're using x. Pi x divided by 40. Let's see, close the sign for me, but I have to close the other, because I've got this open set of parentheses there. So I'll close that, and now I think I got it. If I hit enter, that's it. Okay. exact, but that's for 40 trapezoids, that's what we get. Okay. How close is it? Well, we can compare it and find out. I can just go math. Do you remember what the integral was? Is that like 9 or something? Yeah, 9. Okay. So the definite integral from 0 to pi of sine x we could have done this one analytically a lot faster, couldn't we? What's the answer going to be? 2. Yeah. So we're pretty close. But not exact. Yes, sir.
How do you what's the use of this?
The use of this is,
You don't have programming.
yeah, the use of this is that this is a numerical method for approximate. Before we had graphing calculators, this is how you had to do it.
Using this concept of that algorithmic thing to real life.
Oh, adding up areas under curves? Oh, adding areas. Oh, that's huge. That's huge. Adding areas under curves. Anytime you want to do areas under curves, like in the classic example I think I gave you guys in class was calculated work. If you're adding up the area under a forced displacement graph, that's telling you the actual amount of work that's being done on a system. Right? Yes, sir.
It's also like CAM, when you do, when you use catalyst too.
Yes.
Grouper knows that.
Yep. Yeah, it is. Okay, next time, or next time we talk about this stuff, it may have occurred to you that how do you know if that's how accurate that is? It just gave us some answer. How do we know if n equals 40 was a good choice or not? It turns out there's actually an error formula associated with the trapezoidal rule that can help you decide how many trapezoids you need depending on what kind of accuracy you want. So that's kind of the one hole in our swing here is, well, yeah, that's great, but how do we know if that's any good, right? I mean, n equals 40
Your
was...
exact answer, you can kind of go based on that.
Sure, but what if we didn't have the luxury of a function that we could integrate analytically to compare the two? Because really the reason we have this thing in the first place is for those few cases where we can't find an answer any other way. Assuming we don't have a graphing calculator right there to do it for us, right? And so we need some kind of a way to make a guess or make an estimate of how many trapezoids do we need? What n makes sense? So that's what we need to talk about next time. Yeah.
When did they found this out?
This stuff? Well, calculus was originally, the concept was put together by